My name is Octavio Pacheco, and I am presenting the beamline study for the CubeSat NIAC Phase 3. I worked under the mentorship of Dr. Nick Solomé and Master Trent English. About 100 years ago, there was an issue with one of the most important laws in physics, the law of conservation of energy. Scientists just weren't finding what they were looking for. So then Wolfgang Pauli, he speculated the existence of a new particle that no one had ever thought before, and that it could not be detected. This went against his reputation as theoretical physicist, and he wasn't very happy with this stipulation. But then, about 10 years later, Enrico Fermi, he actually was able to theorize on paper this particle, and he named it neutrino, meaning the little neutral one in Italian. And then, about another 30 years later, in 1956, the Cowan-Rains experiment, those were the ones that detected the neutrinos for the very first time. They used a nuclear reactor instead of nuclear weapons back in the 40s and 50s, and they were actually able to detect these little particles. So, what are neutrinos? Neutrino is a kind of subatomic particle, and as it turns out, it is one of the most common particles there is. They travel through space at almost the speed of light, and they are very, very, very small, about 1 million times smaller than an electron. And they only interact via weak nuclear force. This means that they are very hard to detect, whereas a proton or an electron are polarized, and basically all you need is a magnet to detect them or interact with them. Neutrinos are not that easy. So here I have an example of 3 different detectors that have been built around the world. The one on the top left is IceCube, located at the South Pole. That detector is about 1 kilometer cube in size, and it is 2,500 meters underground. Then on the top right, we have Super Kamiokande, located in Japan, or Super K for short. That detector is also very massive. It requires about 50,000 tons of water to be able to detect solar neutrinos. And then on the bottom, we have Dune. That one is located here in the US. This one is quite interesting because it has 2 locations, one in Chicago in Fermilab, and then the other one in South Dakota. At Fermilab, there is a particle accelerator that shoots particles through Earth, and then there is a 70,000 ton detector at South Dakota that actually receives these particles and then measures them and do whatever they need. Well, as noted, all of these detectors are very, very massive. Okay, so why do we care about neutrinos? Well, neutrinos have contributed to some of the major theories that we now know, like the electroweak interaction. We know that they are produced in fusion processes, for instance, in the center of our sun, where things are very, very, very warm and at really high pressures. And so these make them useful to study stars, starting with our sun. And actually, the picture that you are seeing on the screen right now, on the left, that is a picture the Super K produced using neutrinos of our sun. Well, for this project, what we are attempting to do is to build our detector. And this detector will be launched to the sun because there it will be a lot closer from the source, and we will get a lot more neutrinos. Because with these detectors that I showed you, we do get some interactions, but we don't get that many. And also another thing to notice is that our detector will be significantly smaller. It will be about 2 meters, 2 to 3 meters in size. But well, before actually building that detector that we are going to launch to space, we are building a CubeSat, a even smaller detector, which this will be the size and shape of the detector, where all the electronics are going to be in this portion, and the actual detector portion is going to be just in about this third of the size. So this CubeSat is going to be launched into polar orbit on Earth about 2024. And before we launch it, we are going to take this CubeSat to Fermilab. We are going to place it in the particle accelerator, and we are going to shoot particles at it. This is just to make sure that our shielding, our electronics, and everything works properly, and that our science does make sense. So far, what I've done for this project, everything has been 100% computational. Here I have a couple pictures of the simulations that I've run, where I have some of the main components of my detector. I have, going from the outside to the inside, I have air, then I have a tungsten shield, a V2 array, some PMTs, and the main part or focus of this research is the GA crystal, or what you see here on yellow, that little yellow square. That GA crystal, it stands for gallium, aluminum, gadolinium, garnet. Well, in that detector, we are looking for a specific timing and a specific reaction that tells us that there has been a neutrino interaction. What you see in white there, that is actually the reaction that we are looking for. So, what did I do with these simulations? In these simulations, I'm able to input any range of energies that I want. For this project, I did energy levels from 800 to 4,000 MeV. And then I only use electrons and protons because, again, for this small of a detector, we are not really expecting to detect neutrinos. It is very small. We are just testing our science. So, and protons and electrons do the job. They actually give us that timing and those reactions that we are looking for. Another thing to notice is that for this research, I'm able to rotate my detector as I wish in the simulation. But for this specific research, I only rotated it about the vertical axis, meaning that I only rotated it this way. Once I have input all of these values in my simulations, I then create a C file that which I'm able to get the plots and analyze them. The plots, we are using Geont and Root to get this data and actually manipulate it. And also, I have implemented a mathematical way, the Bhattacharya distance method, in which I am able to compare two histograms and see how close from each other they are. So here are some examples of some of the plots that I got. This is an example of an electron shot at 1500 MeV, and I have 5 different angle rotations and a random angle that I assigned. Here is an example of a proton at 1500 MeV, and I have the same 5 angles and another random angle. Okay, so the Bhattacharya distance method. So what does it do? I use the 2 formulas on the top, and where the dB formula on the top right as the actual distance or how close from each other they are. As example, I have here 2 plots. The one on the left, as you can tell, I have 2 lines, one red line and one blue line. You are able to tell that most of the time they are overlapping. Whereas the plot on the right, I have the same 2 lines, the blue and red, but they are not overlapping whatsoever. When calculating the distance for the plot on the left, I get a distance of 0.006282251, whereas on the plot on the right, I get a distance of 2.11182. Well, if you take the ratio of these 2 distances, that means that the plot on the left, the 2 lines are 330 times closer from each other. What does this mean? Basically, if I have my detector on a space and a particle enters our detector, I'm able to tell from which direction it came from and the energy level and the type of particle. So here I have some of the plots that I used to compare the random angle that I showed you earlier. I didn't know this angle, so I basically created this mathematical method to try to find out what that angle was. For the electron case, I found out that the angle that I was looking for was a 43-degree angle. As you can tell here from the plot on the bottom right, the 43-degree angle has the smallest distance. Here for the proton, same thing, I use the same mathematical method to compare it, and as you can tell, the 46-degree angle has the smallest distance, meaning that that's the angle that the particle came from. Okay, so as a conclusion, so with this Bhattacharya distance method, I am able to detect to the nearest degree how close our particle came through, which is pretty impressive. In the case of the electron, that was an error of 0.12%, and in the case of the proton, that was an error of the 0.22%. So those are very small errors, meaning that our data, or my data, was pretty accurate. Some of the limitations for this project definitely include runtime and memory usage. I use BioShock, the supercomputer here at WSU, and sometimes I had to run this supercomputer for days at a time, and a lot of times I actually hit the maximum memory usage that I am allowed to use as a student. So if I had more memory usage or a more advanced supercomputer, I will be able to even input more data. The future work for this project includes to add more rotations to my detector. Instead of only rotating it like this way, I will add some more rotations in different axes, so my detector is kind of diagonal when my particles enter the detector. Well, another future work for this project is change the components. In science, we improve our technology about every day, and actually the components that I show you have already changed within the last month or two, meaning that I have to update those detections and input some more data. And with that, I conclude my presentation. Well, my results that I have, they are going to be for the particle accelerator, whereas the data that I got, I am then when we go to the actual detector and we get real life detections, we are going to compare the two and basically analyze if the simulations give us the real life scenarios. Just again to make sure that whatever we input in our simulations works, or electronics or shield, and mainly the GAC crystal, that we put the exact components and the exact elements that it needs to be put in there, so we get real data. Well, that's a good question. I was always I I always liked math when I was growing up, and then when I was in high school, I started taking some physics classes, and then I really enjoyed it. And then I told my parents that I wanted to study physics, and then my dad ended up telling me that he always wanted to study physics, but he never told me anything, which I found a little bit ironic that he never told me, and I ended up wanting to do the same thing that he wanted to do.